Hello and welcome. We're going to start discussing the next part of statistical geometry, where we're going to begin talking about the formation index in more detail. At the end of the last lecture, I had left off and I'd started talking about formation. Let me just revisit formation to make sure we have a clear understanding of what I mean when I talk about formation. So we can imagine that there's a paper sheet here, so a particular paper sheet, and it has an overall basis weight. So it has a basis weight that's given by the mass of the sheet divided by the area of the sheet. So if we take the mass of the sheet and divide it by the area of the sheet, we have a basis weight. Now, if we begin breaking this sheet down or cutting this sheet up, and by example we could take this paper sheet and we could just cut it up into a number of different smaller squares, we could determine the basis weight local, or the basis weight for each of these individual squares. So for this individual square, we would have the mass of the square divided by the area of the square. And that would give us our local basis weight for that particular region there. And when we did this, we would find out that, of course, on average, when we added up all of these, they would average out to the overall basis weight of the starting sheet. But each of these different squares here, as we cut this sheet up and looked at it, would have a slightly different basis weight. And that slightly different basis weight is related to the structure of the paper sheet. Now remember, when we're forming a paper sheet, or a non-woven for that matter, this is essentially a random process that's occurring where fibers are falling down onto a screen or onto some sort of forming fabric, and we're building up this paper sheet in a random fashion. And that randomness comes out in the formation index. Now, the formation of your final paper sheet can be influenced, or your non-woven for that matter, is influenced strongly by the processes that you're using. But it's also dictated in part by the inherent randomness of the process. So there's some randomness in this process that we cannot avoid. There's just sort of no way around this, no way to avoid this random component of the process. And in a way, it defines the limits of what we can do in terms of getting a nice, smooth, uniform paper sheet. And that's what we're going to investigate here. We're going to use statistics and the Poisson distribution to examine these fibers falling randomly down onto a grid, relating that to the basis weight of the paper sheet and the local variability in the basis weight of the paper sheet to determine its formation index. So last time we left off and we had talked about a grid where we dropped fibers down onto that grid. So we have this grid here, and we dropped a number of fibers down onto this grid, much like the raindrops that we had dropped as well. Okay, so we drop these fibers down onto the grid and they randomly fall. And in this particular case, instead of tracking the fiber, we're tracking the center of the fiber. So there's a fiber and it has a center. So wherever there's a dot that falls, we can imagine that there's a fiber that fell as well. Now, on average, because this is a random process, the fiber centers here will represent the number of fibers that are actually contained within a given area. Sure, sometimes that fiber will be here and it'll go out into the adjacent square, but over here there'll be another fiber that will be part in and out. So on average, we're going to assume that these fibers will all fall, that the number of fiber centers within a given area is directly related to the number of fibers, or the total fiber length within that particular given area. So how can we determine exactly how many fibers fall? So that's the basic question. If you think back to that problem before, we talked about raindrops falling, and we said there was 10,000 raindrops falling over 100 meters squared. So the 100 meters squared, the area is pretty easy. We can arbitrarily pick that, right? So we can pick that. But you might ask yourself, well, how do we determine how many raindrops fell? In a similar relationship, we said there was 10,000 fibers that fell. Over 100 centimeters squared. how do you determine if there's 10,000 fibers, right? We don't want to take the time to count out 10,000 fibers. This is too labor intensive here. So we have to come up with a way for calculating the total number of fibers that fall over a given area. Now if we begin to think about this, there's a lot of different ways that we can do this, but the simplest way that we might do this is we go out and we determine the mass of a single fiber. So if we know m sub f equals the mass of a single fiber. So if we know the mass of a single fiber, and for simplicity right now let's assume all the fibers are the same. We know the mass of the single fiber, then if we just took the total mass divided by the mass of the fiber, that would equal to the number of fibers in mass m. Okay, again, this sounds pretty straightforward right now. The question might be, though, how would you determine the mass of a fiber? So how do you determine the mass of a single fiber? That might sound tricky, but it's actually easier than you might think. We actually have the ability to measure something, and I'm going to give it the abbreviation X, and we're going to call this the coarseness of the fiber. Coarseness of the fiber. And the fiber coarseness is equal to the mass of a fiber divided by the length of the fiber. So I'm going to let L sub f equal the length of a single fiber. So this is the length of the mass of a fiber divided by the length of that fiber, and where L sub f is the length of a fiber. Okay, so we could redraw this, right, or we could rewrite X would be m sub f over L sub f. And in reality, this is relatively straightforward to determine, a little time intensive, but not that time intensive. And actually is what we do is we have an instrument that can measure the length of the fiber, and we can select a mass of fibers, a whole bunch of fibers actually, and weigh those fibers, put them into this instrument, and count the total length of the fiber, and then divide the total mass of the fiber divided by the total length of the fiber, and you'll get the coarseness of the fiber. Why does this work? Why can I take the total length of a mass of fibers and divide it out rather than just a single fiber? Well, I want you to think just a little bit about coarseness. And coarseness, maybe it's easier to explain in terms of a rope. So if we imagine we had a rope here, it's relatively easy to go down and measure that weight of that rope. And so this rope might have some particular length to this rope, and this rope has a particular mass. So there's a mass to this rope and a length to this rope. And to determine the coarseness of this rope, then all we would have to do is go down to our balance, place our rope on that balance, and measure how much it would weigh. So we'd measure how much it would weigh, take our ruler, measure its total length, and that would give us our mass and our length. And so to determine the coarseness, we would just have to simply divide the mass by the length. Now let's do a little thought experiment here. In this thought experiment here, let's take this and we're just going to cut this rope. And so we're going to cut this rope in half. So the length for this half over here would be length over 2. What do you imagine that the mass would be for this half of the rope? You can probably imagine, right, that you have half as much rope. It would be the mass over 2. So now if we had this rope and we'd cut it in half and we measured the coarseness again, so now we're measuring the coarseness again, so the coarseness would be mass over 2, length over 2, and obviously those would go away and we would have mass over length, and we would get the exact same value as we got when we measured the entire row. So this is sort of a critical thing to keep in mind, that coarseness of the fiber is mass per unit length. And if we change the length of the fiber, the coarseness does not change. So if we take a fiber and we cut it, the coarseness will remain the same, independent of the length of the fiber. So coarseness is a property different from the length of the fiber. And actually coarseness is related to the cross-sectional area and the density of the fiber. I'm not going to get into that, but it's a simple relationship actually. If you multiply the cross-sectional area times the density of the fiber, you'll get the coarseness of the fiber. So it's a measurement actually of the cross-sectional area of the fiber. Okay, so we have here this relationship now where we know the coarseness of the fiber, and that's relatively easy to measure. And I also told you we have an instrument that's relatively easy to measure the length of the fiber. So if I measure the coarseness of the fiber, and I just take that measurement that I have and I multiply it by, well, let me not do that because it gets confusing, and I take the coarseness and I multiply it by the length of the fiber. So if I have mass per unit length times the length of the fiber, the result of this is actually m sub f. Cool, right? So now this is the mass of our single fiber. So this comes up into here where we can talk about the number of fibers that we have. Okay, so the number of fibers that we have, and I'm going to give this the abbreviation n sub f. So n sub f is equal to the mass of a fiber, the total mass, so that's a fiber mass divided by the mass of a fiber, which would be equal to the total mass x times L sub f, or coarseness times the length of the fiber. Now, if we know for a paper sheet our basis weight, so up here we talked about this, BW, right? BW equals basis weight, or mass per unit area of our sheet. And this is a pretty common parameter to have for any paper sheet or non-woven, the mass per unit area. So we have this mass per unit area, or basis weight. If we wanted to know the number of fibers in a square meter, we could simply write the number of fibers in a square meter. We could simply write the basis weight, right? So that's the mass per unit area per unit. Let's say we're using grams per meter squared here. This is the grams per meter squared of coarseness times the length of the fiber. Now, to keep these units correct, we would actually have to multiply this by an area. And I'm going to call this an area of inspection. And if we let the area of inspection equal 1 meter squared, this would allow us to determine the number of fibers inside a square meter. So to determine the mass of fibers, all we have to do is multiply by the basis weight. So the basis weight times the area of inspection. So A sub I is equal to the area of inspection. How big of a paper sheet are you going to look at? And we can arbitrarily choose that area of inspection as we so desire. So now once we know the number of fibers, or the total number of fibers that are falling onto an area of inspection, now we would like to determine exactly what the average number of fibers are that fall. Let me go back here. I'm actually going to change this because this is let me go back just a little bit here, and I'm going to revise this. I'm going to revise this particular formula just slightly. And for right now, I'm going to get rid of the area of inspection, and I'm just going to call it an area. Okay, so let me go in here and remove this, And so now we're going to have just simply an area.